Hello! In this video, we're going to look at integrating over some interesting regions using change of coordinates. So specifically, we're going to be using cylindrical coordinates in this first problem and spherical coordinates in the second problem. So in this first one, we're integrating x squared z on the region bounded by x squared plus y squared equals 4z squared, z equals 1, and z equals 2. And the first thing you should know about this is that this x squared plus y squared equals 4z squared, that's a cone. So what's that going to look like? That's going to look something like, we'll have the x-axis out here. It's going to look, well, to help me graph it, let's go ahead and convert this to cylindrical coordinates first. Because cones kind of just make more sense in cylindrical coordinates. They make more sense in cylindrical coordinates than, say, spherical coordinates or rectangular coordinates. So what do cylindrical coordinates look like? They look like x equals r cosine of theta, y equals r sine of theta, and z just stays the same. And then the other thing about cylindrical coordinates is that my dv, the dx, dy, dz part, that's going to turn into r dr, d theta, dz. So we get an extra r when we integrate. So, okay, let's go back to what we were doing. We can then turn this formula into cylindrical coordinates by changing x squared plus y squared. That's going to be r squared cosine squared plus r squared sine squared. That's going to just be r squared equals 4z squared. And to get that r equals plus or minus 2z, which is what we're going to use. But you could also write this as r over negative 1 plus or minus 1/2 r equals z. And that might be useful if we're trying to sketch this cone. Because then I could think I have a radius of 2. The radius is how far out I am from the z-axis. And then I have a radius of 2 when z equals 1. Or you could say when z equals 1, or when the radius equals 1, I have a z of 1/2, something like that. But all that does is that lets you figure out what your radius is going to be. And we get a cone that goes out this way, technically also this way. I'm not going to draw all of that super much, but that is the general idea of what our cone looks like. And this equation, especially with the plus sign, is what we're going to want to focus on. Because we're going to try to set up a set of inequalities here to describe this region. Because I want to integrate over r, theta, and z. So I need to know what r is between, what theta is between, and what z is between. And this equation here tells us that r equals plus or minus 2z. Basically, this radius, how far out can I go out from the z-axis? Well, that's going to be at most 2z, because this is the line r equals 2z. And my radius can be at most that. But if we're just talking about distance, it doesn't really make sense to talk about negative distance. So r is going to be greater than or equal to 0. And we'll see another reason why we don't care about negative distance when we look at theta. So theta is telling me how far away or how far around am I rotating. And I have the whole cone here. So if I start at the x-axis and go to the y-axis, I'm having, this would be 0 to pi over 2. But I'm also going back, then I'm also going here, and then I'm also going here. So I'm actually going the full 360 degrees or 2 pi radians. The reason why I don't need negative values for r is because those are taken care of when theta equals pi. When theta equals pi, I'm facing the opposite direction and I'm getting this left-hand side of the cone. Technically, that's actually at 3 pi over 2 if we, start there. All that, etc., etc. But the gist of it is, since we're going all 2 pi radians around, I don't need to worry about having negative r values there to kind of describe this cone shape. And as far as my cone goes, it doesn't really tell me what z is going between, but this part tells me that z is between 1 and 2, so I have those bounds as well. And with that, I'm ready to set up a triple integral. So I'm going to be integrating from z is between 1 and 2, theta is between 0 and 2 pi, r is between 0 and 2z. And since I'm turning this into cylindrical coordinates, I also have to turn this into cylindrical coordinates. So actually, let's take a step back and kind of just look at everything that we start with and then what we're going to turn it into. I start with a general triple integral over some region W of x squared z dv. And now I need to change all of those things. Z is going from 1 to 2, theta is going from 0 to 2 pi, and r is going between 0 and 2z. X squared is going to turn into r squared cosine squared theta. Z is going to turn into z. It's going to stay the same, actually. dv is going to turn into r dr d theta dz. And just to save myself having to write this an extra time, that r squared and that r cubed, that r squared and that r are going to come together to form an r cubed. And now I'm ready to evaluate a triple integral. So let's start by taking the antiderivative of just r cubed, this cosine squared theta z, that's all a constant right now. So I kind of ignore that. Antiderivative of r cubed is r to the fourth over 4. We'll keep the cosine squared theta z around. We're going to evaluate that from 0 to 2z. When I plug in 0, I get 0, so nothing interesting happens there. But when I plug in 2z, this is going to turn into 16z to the fourth. That 16 and that 4 are going to cancel, leaving me with the integral from 1 to 2, 0 to 2 pi. This will just be 4z to the fourth cosine squared theta z d theta dz. And hold up, I have a z there, I have a z to the fourth there. Let's go ahead and put those together, giving me z to the fifth. Okay, so we're making some progress. Next I have to integrate theta, which is going to be a little tricky because I have a cosine squared. But what we know is that cosine squared equals 1 plus cosine of 2 theta over 2. And if I make that replacement, what I end up with instead is the integral from 1 to 2, the integral from 0 to 2 pi, 2 z to the fifth, 1 plus cosine of 2 theta. And that is much easier to integrate. I can treat this whole 2z to the fifth as a constant, and then just integrate what we have left. This 1 plus cosine of 2 theta is going to turn into theta plus sine of 2 theta over 2. And evaluate from 0 to 2 pi dz. What we notice is when I plug in 0, this part is 0. And when I plug in 2 pi, this part is 0. So that's just all going to go away. Theta, on the other hand, is going to be 2 pi at 2 pi and 0 at 0. So this will just all end up being 4 pi z to the fifth dz. Integral from 1 to 2. That 4 pi is just a constant, so I can maybe pull that out. And then we're going to integrate this other part. We'll get z to the sixth over 6, evaluated from 1 to 2. That's going to be 4 pi. In fact, that's going to be 4/6 pi, or maybe 2/3 pi. And that's going to be z to the sixth, so 2 to the sixth is going to be 64, minus z to the 1, that's going to be 1 to the sixth, that's what I meant to say, 1 to the sixth. So this is going to be 2/3 pi times 63, which ends up being 42 pi. And that's my integral. Okay, so setting up the integral was hard. And then evaluating the integral was hard, but we ended up getting the answer here. What you don't know is that this is like my fourth take making this video. So there's a lot going on here, but we can get there in the end. With that, let's move on to the spherical coordinates, which at least is a little bit easier to interpret what this is going to look like. So I'm going to go ahead and draw my axes. I'm not going to attempt to draw this region because I'm not great at drawing spheres, but I'm going to keep this up here for when I'm talking about my rho, my phi, and my theta. So I want to integrate x squared z over this region in the first octant between spheres of radius 1 and 2, and I want to integrate that in spherical coordinates. What are spherical coordinates? Well, spherical coordinates include rho, sine of phi, cosine of theta, y equals rho sine of phi, sine of theta, and z equals rho cosine of phi. And then dv is a little bit more complicated. That's going to end up being rho squared sine of phi d rho d phi d theta. So a little harder to remember, but there you go. And you get that, and this for that matter, by taking the Jacobian of this transformation. So what's this going to look like? Well, what's rho going between? I'm between spheres of radius 1 and 2, so my distance from the origin is going to be between 1 and 2. And rho is just my distance from the origin. What's phi going between? Well, I just want stuff in this first octant. So if we imagine some point on the z-axis, I only want to rotate down a quarter circle. So we're only going to rotate, this represents my phi. Phi is only going up to pi over 2. Similarly, for theta, that's asking how far am I rotating around this way. I'm also only going a quarter turn. So that's also going to be between 0 and pi over 2. So let's go ahead and set up my integral. This here is going to turn into the integral from 0 to pi over 2, the integral from 0 to pi over 2, the integral from 1 to 2. X squared is going to turn into, this is going to be a doozy, rho squared, sine squared of phi, cosine squared of theta. Z is going to turn into rho cosine of phi. And then dv is going to turn into rho squared sine of phi d rho d phi d theta. And that looks awful, but it's actually going to simplify quite a bit. I have rho squared and a rho and another rho squared. That's a total of rho to the 5th. I have a total of sine cubed phi. I have a cosine of phi. And I have a cosine squared of theta. d rho, d phi, d theta. Okay, and actually that's not as bad as it looks. Let's start by integrating rho, because that's the easy part. We'll have the integral from 0 to pi over 2, integral from 0 to pi over 2. This will be rho to the 6th over 6. Everything else here is a constant. So we'll still have sine cubed of phi, cosine of phi, cosine squared of theta. That's going to be evaluated from 1 to 2. And then we'll have d phi, d theta. And if we look at this, I'm not going to do all the drudgery work, but this is going to be similar to what we just did. 64 over 6 minus 1 over 6, so 63 over 6, which equals 21 over 2. So basically when I take this net change, I should end up with 0 pi over 2, 0 pi over 2. 21 over 2 sine cubed of phi cosine of phi cosine squared of theta d phi d theta. And now you see a lot of trig, and it looks a little scary, but it's not as bad as it looks, especially because we're only looking at phi right now. And if I look at phi, I notice that I can do a little u substitution, where u equals sine of phi, and du equals cosine of phi d phi. So that's actually going to allow me to deal with this. It might feel a little weird to do u substitution in the middle of a change of variables problem, because change of variables is kind of our generalization of u substitution. But, don't worry about it too much. You can still use your standard integration techniques. We just have change of variables as like a superpowered integration technique. So I could do this. I'm going to kind of skip ahead. I'm not going to write out the u substitution, because this is one where the substitution is actually about as nice as it can be. This is just going to turn into u cubed du with some other stuff thrown on. So that's just going to integrate to u to the 4th over 4. So we'll end up with sine to the 4th of phi over 4. We still have a cosine squared theta, and this is being evaluated from 0 to pi over 2. And then we still have a d theta. When I plug in 0, sine to the 4th is going to be 0, so that won't matter. But when I plug in pi over 2, this is going to be 1. So what that really just ends up being is 0 to pi over 2. This is going to be 21 over 8 cosine squared of theta. D theta. And we can do almost the exact same trick that we did last time with the change cosine squared to 1 plus cosine 2 theta over 2. So that's going to turn my integral into the integral from 0 to pi over 2, 21 over 16, 1 plus cosine of 2 theta over 2. Nope, not over 2. Just cosine 2 theta. I took care of the over 2 by multiplying my denominator by 2. When I integrate that, I have to be a little bit more careful than I was last time, but it turns out not too much more careful. I'm taking the integral, so I don't need to write that again. Of 21 over 16 theta plus sine of 2 theta over 2, evaluated from 0 to pi over 2. And we do need to be a little careful, because this sine of 2 theta, when I plug in pi over 2, it does still equal 0, because sine of pi is 0. But it's good to check. So when I plug in pi over 2 at 0, when I plug in 0 at 0, so this sine over 2 theta over 2, still not doing anything. So I can still ignore that. And then really all I have left is this theta, which basically will just turn into a pi over 2, because when I plug in 0, it goes away. And I'm left with 21 over 16 times pi over 2, also known as 21 over 32 pi. And that would be my integral in spherical coordinates. So, spherical coordinates and cylindrical coordinates can be a little intimidating. The integrals can get a little bit messy, but they are nothing to be terrified of as long as you're able to deal with some of your trig functions. You should be fine. So there you go. There are some integrals using cylindrical coordinates and spherical coordinates.